guys, welcome back to Explore Electronics Plus. So let us continue our discussion with respect to synchronous FIFO verification. In this previous video of part 1, I have explained the UVM environment and also we have seen the code with respect to the interface, sequences and also the different tests what we are going to perform here. And we have simulated the two tests, that is random test as well as the write test, right? Let us continue our discussion. So through this test bench, we are verifying the FIFO with 5 different test cases. The first one is random test, which we have seen already. Second one is write only. Here we are expecting all the locations of the FIFO, that is depth of the FIFO is reached. We are expecting the full condition that we have seen. Now let us run this back-to-back write read test. So this test I am triggering here through run test, that is FIFO underscore write underscore read test. You can see here, this is the test code I have, class FIFO underscore write underscore read test, extending from FIFO test itself. Here is my basic FIFO test, right? I am extending from there. And in this, the build phase, you can see I am creating the object of the sequence. The sequence which I am using in this particular test is FIFO write read sequence. So in the run phase of this particular test, I am raising the objection and I am starting that particular sequence, right? Which sequence it refers to means FIFO write read sequence. Here I am starting that on the sequencer. So now let us understand what is this sequence consisting of, write read sequence. In the sequence, you can see I have a class FIFO write read sequence extending from UVM sequence, and I am saying this sequence item I am using. So in this particular sequence, I need to generate the values in such a way that in one cycle, it should write into the FIFO. In the next cycle, I need to read the data. So for that, you can see in the task body of the sequence, I am using a standard macro of the UVM, which do the functionality same as which we have seen previously, like creating the transaction object and then wait for grant, randomize, send request and wait for item done. So this is the line of code what we are going to write in a body method of the sequence to communicate with the driver and randomize the things and giving it to the driver for further functionality. Or we are going to use a start item, randomize and finish item. This line of codes can be automated by using UVM do with. That is what I am utilizing over here in the write read sequence. Here first I am doing UVM do with. REQ is the default handle for the transaction item, and then REQ.write is equal to 1 means I am keeping write transaction here and read is equal to 0 means write signal is 1 and read signal is 0. I am keeping here means while doing the randomization only write is equal to 1 will happen and the randomized data will go to the FIFO and the write will happen. And in the next cycle, I am calling this method again to generate the data with read is equal to 1 and write is equal to 0. So this will be repeated for 5 times. It means first cycle it will write, in the next cycle it will read. Again, the second set of transaction will write and read. So this will be repeated for 5 times. Let us run this code and see. By using this method, we are able to achieve the write and read back to back. And this line of code is used for avoiding the error when the response queue is full. I am disabling it, or you can increase the depth of the queue by using this line of code also. You can see here is the back-to-back write and read transaction. In the first cycle, I am making write is equal to 1 and the value it is generated is 134. It is writing into the FIFO. In the next cycle, I am making read is equal to 1 and it is taking 1 cycle delay to read the data and put it into data out. You can see 134 is the data out coming. And at the same time, I am writing 124 and I am reading it over here. This continues and here we are expecting a empty condition at the initial stage, and also once we read that data, again empty condition will be 1. So this is what we are expecting and it is behaving correctly. And in this case, never FIFO will get filled. That's why full condition will be 0. Why? Because we are writing into one location and we are reading it back. So FIFO will not be full at all. And in the next test case, if you see, we'll be having write complete then read. So this test I have it over here. You can see FIFO write then read. In this test completely I will write the data into the FIFO. As soon as it reaches the depth as 8, we will be getting the full condition, and then I am reading it completely, and we are expecting the empty condition after reading 8 values. So again the same methodology here, write the objection, start the sequence through this on the sequencer. And also you can see one more line of code here, that is phase done dot set drain time this comma 50. Here this is a extra time we are giving into the run phase to complete the driver monitor sequencer and scoreboard functionality. Sometimes the DUT may take some time to give the response. As we seen in the waveform, it take one more clock cycle delay to give the data out. Memories will do that, and to process that into the scoreboard and all, we may take one more clock cycles. In such cases, we require some more time in the run phase. That's why here we can set a drain time of extra 50 time units. That is what I have added over here. And let us see the sequence code of this FIFO underscore write then read sequence. That is which I am using over here. In this sequence code, you can see write then read. Yeah, I have it over here. So this sequence will be having a write sequence and read sequence inside. Means I have a separate write sequence and separate read sequence, and I am creating a handle as write sequence and read sequence like this. And inside a body method, you can see I am utilizing tick UVM do macro. This will do the start, create and finish functionality, and I am passing this sequence as an argument. So this is a sequence inside a sequence, right? This write sequence we are utilizing inside a write read sequence. So now once this body method is called, we are triggering through the test over here. Once this sequence is started, here tick UVM do will call the write sequence inside. Here I will be having a write sequence. So this sequence will be having a body method again. So here I will be creating the item, and I am utilizing start item finish item method to create the transaction. Here item dot randomize with write is equal to 1 and read is equal to 0. This will do only the write operation. Means I am blocking the read operation here. It means in this write then read sequence, I will be having a body method. Inside that I will be having a write sequence. Once it calls the write sequence, here I am repeating this for 8 times, means 8 write transactions will be created, right? So this will do 8 writes. After 8 transactions, the depth of the FIFO is reached, we will be getting the full condition. And then once it completes its operation, the next line of the code is read sequence triggering. Here it will call the read sequence. In the read sequence, I am using a standard method, that is tick UVM do with read is equal to 1 and write is equal to 0. Again I am repeating this for 8 times, so 8 read transactions will happen, right? And by using this method, we can utilize a sequence inside a sequence to do the write transaction first and then read transaction, right? So now let us run this code and see whether we are getting the full condition after the 8 writes and we are getting the empty condition after 8 reads. So this is the waveform for this particular test. Initially empty condition will be 1 and we are doing the write into the FIFO, write is equal to 1, and these are the different values. After 8 values we have written into the FIFO. You can see here a full condition is 1. This is a full flag is 1 and empty will be 0. And we start reading the data from here, read is equal to 1, and from the next cycle we are start getting the data, and after 8 values we got from the FIFO, FIFO is saying it is empty by giving empty signal is equal to 1. So by this way we can verify the complete depth of the FIFO we can reach and get the full condition, and also we can get the empty condition when we read that completely. So with this, let us see the driver monitor and scoreboard code also. And already we have seen the driver code. Here in the run phase of the driver, what we are doing, first we are creating the transaction object, and sequence item port is a standard port of the driver. Through that, we are requesting a next item from the sequencer. That sequencer will pass that information to sequence. So here this trans is the transaction object what we are operating with, and we are requesting to the sequencer, right? And we are waiting for one clock cycle to drive the values into the interface signals. Here we are doing the conversion from transaction packet to the signal level. You can see at my right, I will be having all the trans signals, and at the left, we are assigning these transaction packet signals to the individual signals of the interface. This driv underscore interface is a macro which I have created here that will refers to the clocking block, driver clocking block in the interface. So this driv.if refers to the interface signal. When trans.write is equal to 1, then only we are going to provide write, read as well as data in. If trans.read is equal to 1, no need to provide the data in, we just provide the write and read information, that is write signal and the read signal into the interface. After providing this, we need to put that into the port again, sequence item port, item done, the transaction is completed, driver has given that to the interface, and again it will request for the next set of data. This is what the driver is going to do. This is a simple driver functionality here, which we are converting a transaction level packet information into the signal level. Next one is monitor. In the monitor, we are expecting the FIFO to perform its operation and giving back the data to the test bench. So here the FIFO monitor extending from UVM monitor, it will be having a port again that we need to define it ourselves. A standard port is not available. We need to create it using UVM analysis port. Here we need to pass the type of the transaction type we are operating on this port. FIFO sequence item is the transaction, and the name of the port which I am creating here is AP. Okay. So now this is a standard constructor. In the build phase, we need to have an interface access over here in the monitor to get the signals from the DUT. That's why again a config DB is required here to get the interface handle as VIF, right? Here we have defined the virtual interface over here. So this is virtual because a interface is a physical interface. Inside a class, if we are utilizing that, means we need to define it as virtual. Then only we are able to access the signals of the interface inside a class. So that we do in a build phase. So here we need to understand what we do in the run phase of the monitor. Run phase of the monitor here, forever begin. In the driver also we will be operate that with forever begin. In monitor also forever begin. First we need to create the object of the transaction type, that is trans here, and whatever the signals we are getting from the DUT, that will be putting into the transaction. If you see, this is trans.write will be equal to tick mon underscore interface is a macro which is pointing to the clocking block. So that is directly assigned to the transaction. Here trans.data in and trans.full, trans.read, data out, empty. All the signals we are taken from the interface and creating a packet. If you see the driver, you will not see the full and empty conditions and the data out. Why? Because these are the outputs from the FIFO that we are taking into the transaction in the monitor. In the driver, we will be driving only the inputs into the interface, right? So this is the code of the monitor. And again, wait for the one more clock cycle. And after the packet is constructed over here, wait for one cycle. And we need to call the write method. This is the standard write method we need to implement in the scoreboard. You can see the definition of this write method in the scoreboard, where the transaction packet what we have created will be put it into the write method through a port of the monitor. The monitor port is analysis port, that is AP in our case, AP.write of trans. Means we are making this transaction packet and giving it to the scoreboard through this. Now let us understand the scoreboard. FIFO scoreboard extending from UVM scoreboard. And here also we need to have one port, that is UVM analysis implementation port. This requires two arguments. One is the sequence item type and also the name of the class itself. And the name of the analysis implementation port of the scoreboard is SCB underscore port, which I am taking here. So you can see this port and the monitors AP, which is connected in the environment. You can see environment connect phase. In the connect phase of the environment, we have connected those two ports, monitors analysis port and the scoreboard port, that is SCB underscore port, right? Now, in the FIFO scoreboard, we should have a method called write, right? Which we have used over here, which we are passing the transactions through the write method. You can see the definition of the write method over here. It is function write. It is expecting one argument, that is transaction type, right? That we have passed through in the monitor, which we are calling in the monitor and passing the transaction. Here the transaction is available and we need to put it into the queue. Here we are defining a queue which is of type sequence item itself, and into the queue we are putting all the transaction what we are getting from the monitor every time, right? And we are pushing back, means we are utilizing a pushback functionality of the queue and pushing the data transaction into the queue. This is the write functionality. And in the run phase, we need to write the comparison logic and we need to say whether the data is expected match or the failed match. So to do that, first thing is we need to take the data which is coming from the monitor into this queue, right? Now this queue will be having all the transaction. In the run phase, the first thing is we need to check whether the queue is filled, at least one data is come or not. So for that, wait for the queue size becomes more than 0, and we are taking that into the trans handle. Trans is the another handle of the transaction itself. So to this trans, we are popping out the data from the queue. Pop front trans means whichever the first data which we push back will be available if you do the pop front from the queue. So that is available in the transaction trans now. In this trans, we will be having all the information like write, read, data in, data out, everything. If it is write is equal to 1, if write is equal to 1, what we are doing, while writing we will be having the data ins, whatever the data which we have generated, that we are keeping into a memory. This memory is also a queue over here. You can see a definition declaration of memory over here as a queue, and this memory will be containing all the data ins. Whenever the write transaction is 1, write is equal to 1, the data what we are getting into the queue will be taken out over here and putting into the memory. Means all the data ins will be present in this memory now, right? And when we are doing the read functionality, then only we can compare the data out coming and with respect to the data in what we have in the memory now. To do that, and as we know, the transactions coming out of the FIFO will be having some delay. So to handle that properly, we will be having an internal signal called read delay clock. Whenever this read delay clock is equal to 1 and trans.read is equal to 1, then only we will be performing our checking. So to do that, I am checking here whether trans.read is equal to 1 or read clock is not 0. Any one of this is true, we will be entering into the block of code under if, right? And again I am checking if read clock is equal to 0 or 1. If it is 0, I am making that to 1 first, and I am not checking at that time. I am again coming back to the if condition and again checking read is equal to 1 still, and read clock, which I am making it as 1 here, will satisfy. If this satisfies, again it will enter into the block of code under if, and this condition fails now we will be entering into the else part. In this else part, I am just checking the read condition once again to make the delay clock is equal to 0. If it is 0, this condition will not be true at all. Why? Because once we enter into the else part, we are assuming that read is equal to 1 and clock is equal to 1, right? Now this is the logic for checking the data in and data out. Now all the data in will be available in the memory and all the data out will be available in the trans, right? Now you can see here we are checking this memory will be containing some data or not. So if this size is more than 0, we are taking that memory content which is data in into tx.data, tx underscore data. This will be having data in now. We are comparing that tx.data, that is nothing but data in, with trans.data out. This trans.data out, in the sense it is directly from the queue, right? This mem will be having only data in, means tx underscore data in the sense that is data in, trans.data out in the sense that is data out. If this is true, if this is equal, if these two are equal, we can say there is a expected match. If this fails, there is a failed match, and we are printing all the values of tx data and data out. Tx data in the sense that is data in, and this is data out. You can see in the scoreboard output over here, you can see the first thing is expected match, the value is 151, and data out is also 151. You can see over here the first value is 151 and the data out is also 151, and the second value is 4 and the received data is also 4. And if you see, the second value which we have written is 4 and data which we are getting back is 4. So this continues, it will give all the matches perfectly. If it fails, we need to see our DUT is functioning correctly or not, right? This is how we can implement a simple scoreboard to check the data which we have written and also the data coming out of the FIFO is correct or not. This functionality may be different from person to person. If you have implemented any other logic to have a checker logic over here, please comment below. And this is one of the method to do that. And every time once we do that, if this fails, we are making the read clock is equal to 0 and it continues. For all the transactions of the FIFO, we will be executing this once and it will generate the expected match or the failed match condition. Now let us see one more test case, which is back-to-back read-write. In the back-to-back read-write case, we will be having one cycle write and one cycle read. So here we will be having first writing the value, that is 134. 134 is coming out. Then we are writing 124. 124 is coming out. Then 66. 66 is coming out. Right? So that is what the expectation now. From the scoreboard, you can see 134, 134, 124, 124, 66, 66, 216, 216, 62, 62. These are the 5 values which we have generated, and the 5 values we have retrieved from the FIFO. This is the way we can use different test cases to perform the testing operation on this particular FIFO. You can have multiple test cases like this, and also you can pass the name of the test which we are triggering from the run option over here, right? So this is the simple UVM test bench for the FIFO verification. You can also write the other test cases as per your requirement. You can write only 3 values and read it back. You can write 3 values and try to read 4 values. Those are the different test cases we can perform on FIFO. Let us discuss further on different DUTs and the verification aspects in a further video. I will stop this video here. This will help freshers to understand how actually the UVM test bench look like and how to perform the different tests in a simple way. Thank you.